Greetings from New York University. My name is Aborno Iceberry, and welcome to Physics 3. Today's topic is the spring mass system. Alright, so you might say, hey, wait, I learned that in Physics 1. Well, you'll be surprised at just how complicated a spring mass system can get. So here, it's simple. You've already seen this before. You've got a mass, and you've got a spring, right? So the spring has an equilibrium position that it would normally be at. But now there is a disturbance of delta x in the way. So as the cameraman has said, that means that the restoring force on the spring will be in the opposite direction of this disturbance. But that's not all. Some springs are... Give it a second. Some springs are stiffer or lighter. So some springs take more force to cross. Some springs can be crossed easily. So, for example, if you have, I don't know, the springs on a toy or the spring on your car's damper, that is very hard to break or very hard to stretch and squeeze. You need to exert a lot of force to make it stretch just a little bit. But, for example, a slinky, even a baby can stretch that one. So that means that different springs have different stiffness constants, or what we like to call spring constants. And this is just K. So now this course actually relies very heavily on ordinary differential equations and partial differential equations, as it will be discussing the behavior of waves and oscillations. And this is the simplest oscillation, simple harmonic motion. So this is Hooke's law, right? But now it's about to get a little bit more complicated. Now, you've been taught, and probably shown too, if you're in a physics class worth its salt, that if you disturb a spring, it will oscillate repeatedly. So you've never actually been given a reason for why this is the case, but you're about to be given a reason now. We all know Newton's second law is very iconic. But now what we'll be doing is we're going to be considering everything else as a constant, like m and k, and x as a function of time, which is our variable. So what does that mean? Well, that means that acceleration is just the double derivative of x. And by extension, velocity is the single derivative. So what does that mean? Well, that means we can write this as mx prime prime instead of ma. And how does that help us? Well, the only major force horizontally on this guy, that's not moving vertically, of course, because these two are balanced, the only force horizontally, assuming no friction, is gonna be Fs. So that means that this minus k delta x, or minus kx, to keep it short, assuming that the equilibrium position is x equals 0, kx is equal to that net force, mx prime prime. So then all we have to do is subtract mx prime prime from both sides. And just to make this a little bit nicer, I'm going to make everything positive. All right, so then what do we do? Well, you'll notice this is actually a very easy equation to solve. Why? Well, if you've ever taken ordinary differential equations, this is probably flashing in your head right now. But for those who don't know, I'll give you a little bit of an explanation. So essentially what we have here is a constant times the double derivative plus a constant times the actual function. So if we go back to the original, this is essentially saying the original function, or rather the double derivative of the function, is equal to the original function times some irrelevant constant. So essentially what we want to do is we want to find some function such that its double derivative is proportional to itself. And so the two things that pop up into your head are probably going to be the sinusoidal functions and the exponential function. Now, actually, the people in my physics 3 class didn't know what imaginary numbers were, so we're going to have to cross this out for now. But let's talk about cosine x and sine x. So, of course, we all know that when taking the derivative of sine of...
You didn't mention that to talk?
No, because that would be rude. If we take the double derivative of this, what does it give us? F cosine fx and f squared minus f squared, in fact, sine fx. And the same thing if we swap cosine for sine. So these two are going to be our critical functions. Mx prime prime plus kx is equal to 0. So essentially, we want to find a function that satisfies this relation. So what does that mean? Well, if x of t is really equal to sine of ft, then how is it going to satisfy our equation over here? Well, we take the double derivative, and that's going to give us minus f squared sine ft, which means that minus f squared has to be equal to this constant in front, minus k over m, which means that f has to be equal to k, or the square root of k over m. This is why we call this angular frequency, which is actually represented via omega. So this is the frequency of our spring, how often it oscillates, going from side to side to side to side. All right, so then we have finally solved it, right? Is that all we need to know? The answer is sine omega t, where omega is rad k over m. Well, actually, no. We can add some more to it. One thing you may have noticed is that, well, if I multiply a, some constant, by x of t, then the second derivative of it will also be multiplied by the same factor. Which means in this proportionality relation, all we have to do is we can multiply x and x double prime by any constant we want, and it doesn't matter, it's going to still work. And you might ask, well, how is this relevant? Well, if you've ever messed around with sinusoidal functions in graphing calculators, you'll notice that a regular sine function might look like this. But when you multiply it by 2, you get this. When you multiply it by 3, you get this. You get bigger oscillations. And now is the time to make a physical observation. When you pull the block farther, what does it do? It oscillates more, which means when you pull the block farther, that's actually indirectly setting the amplitude of this wave. So really, what's going on here is we have x prime x is equal to x initial times sine rad k over m. Well, I'll just abbreviate it, t. But in fact, that's not all either. Why? Because, of course, cosine also works with this. And they don't even have to be the same constant either. But this simplifies to a sinusoidal function anyway. So it doesn't quite matter. So what we're going to do is we're going to keep it actually. It's sine of omega t times x naught for now. So this is how we solve a simple spring system using an ordinary differential equation. Thank you everybody for watching, and we'll see you in the next one.